Welcome to another deep dive into the fascinating world of chemistry. Today, we're going to be exploring this fundamental concept called the reactivity series.
Yeah,
You know,
reactivity serum.
it's kind of like a ranking system
Right.
that tells us, which metals are like the most reactive and which ones prefer to just sort of stay put.
Yeah, it's all about how easily metals lose electrons to become positive ions.
Yeah.
So some metals are, practically throwing their electrons at anything that comes near them, and others are holding on for dear life.
So it's almost like a game of hot potato
Exactly.
with electrons
Yeah, exactly.
instead of, potato.
The metals at the top of the reactivity series, like potassium and sodium,
Right.
they're the most eager to lose those electrons.
Uh-huh.
They'll react explosively with water,
Oh, wow.
even with the air.
Really?
And then as we go down the series, the metals become less reactive.
Yeah.
So something like gold, for example, is
Yeah.
at the bottom of the list. It's very stable. It doesn't react easily.
That makes sense.
Yeah.
Gold doesn't tarnish
Right.
or corrode, really.
Yeah.
So it's perfect for things like jewelry and stuff.
Yeah.
But what about those other elements that I see on this reactivity series chart?
Okay.
Like carbon and hydrogen.
Yeah.
They're not metals.
You're right. They're not metals,
Right.
but they play a crucial role in the reactivity of metals,
Okay.
especially when it comes to extracting metals from their ores.
Interesting.
So that's why they're included in the series.
Okay, so how does this whole reactivity thing, work in practice?
Right.
What happens when a metal reacts?
Well, when a metal reacts, it loses electrons
Right.
and forms positive ions.
Okay.
This process is called oxidation.
Oxidation.
And for a metal to be oxidized, something else has to gain those electrons.
Okay.
And that's called reduction.
So oxidation and reduction, they always go together.
Always. They're like
Yes.
two sides of the same coin. One substance loses electrons oxidation,
Right.
while another gains them reduction.
Okay, so the reactivity series, it tells us which metals are most likely to be oxidized.
Exactly.
So the higher up in the series,
Yeah.
the more readily they lose electrons.
Exactly.
Okay, so the metals at the top of this series, those are the ones that are the most likely to react and undergo oxidation.
Right.
But what makes them so reactive in the first place?
It has to do with how strongly their outermost electrons are held. Metals at the top of the series
Yeah.
have electrons that are relatively loosely bound,
Okay.
so they can be easily lost.
Right.
As you move down the series, the electrons are held more tightly,
Uh-huh.
making the metals less reactive.
So the reactivity series, it's not just about how metals react with water.
Right.
It's about their tendency to lose electrons and undergo oxidation
Exactly.
in any reaction.
Yeah, it's a fundamental concept that helps us understand
Right.
a wide range of chemical reactions.
Yeah, this is already giving me a much better understanding of,
Yeah.
how metals behave.
Yeah.
But we're going to be back in part 2 to explore some more.
Great.
Welcome back to our deep dive into the reactivity series.
Yes.
In the first part, we talked about how this series helps us understand, the tendency of metals to lose electrons
Right.
and undergo oxidation.
Yeah.
But what does this all mean for how metals actually interact with each other?
Okay, well, that's where things get really interesting.
Okay.
The reactivity series helps us predict what happens when one metal comes into contact with another,
Okay.
specifically in something called a displacement reaction.
Okay, so let's unpack this a little bit.
Yeah.
What exactly is a displacement reaction?
Okay, so imagine a dance where everyone has a partner.
Okay.
A displacement reaction is kind of like someone cutting in and stealing another person's dance partner.
Oh, okay.
In chemistry terms, a more reactive metal can displace a less reactive metal
Okay.
from a compound.
So it's like a chemical competition for partners.
Exactly.
And the more reactive metal always wins.
Exactly.
Okay.
So let's take an example. If you put an iron nail into a solution of copper sulfate,
Uh-huh.
something fascinating happens.
Okay.
Iron is more reactive than copper,
Right.
so it will displace the copper from the copper sulfate,
Okay.
forming iron sulfate and leaving the copper metal behind.
Oh, wow.
So you would actually see a reddish-brown deposit of copper forming on the iron nail.
So the iron is essentially kicking the copper out of its compound and taking its place.
Exactly.
That's pretty cool.
It is, and this principle has some real-world applications.
Okay.
Displacement reactions are used in various industrial processes,
Mm-hmm.
like purifying metals or recovering valuable metals from waste.
So it's not just, theoretical chemistry. This actually has practical uses.
Exactly.
But I'm curious about something you mentioned earlier, that carbon and hydrogen are included in the reactivity series, even though they're not metals.
Yeah.
How do they fit into these displacement reactions?
That's a great question. Carbon, in particular, plays a critical role in extracting metals from their ores.
Okay.
Most metals are found in nature, combined with other elements like oxygen, in the form of metal oxides.
Right.
To get that pure metal, we need to separate it from the oxygen.
So how does carbon help with that?
Carbon is a powerful reducing agent, which means it's very good at giving up electrons. In the context of metal extraction, carbon can donate electrons to the metal oxide, forcing the oxygen to detach from the metal.
Oh, wow.
This leaves behind the pure metal.
So carbon is like a chemical superhero, freeing the metal from its oxygen prison.
Exactly.
But can carbon be used to extract any metal?
That's where the reactivity series comes in again. Carbon can only extract metals that are less reactive than itself.
Right.
For metals higher up on the series, we need other methods. But carbon extraction is a very common and efficient method for many important metals like iron.
This is all so interconnected.
It is.
The reactivity series helps us understand not just which metals are most likely to react, but also, how we can extract them from the earth.
Exactly.
I'm starting to see how fundamental this concept really is.
It is.
But before we move on to part 3, can we just revisit those terms? Oxidation and reduction.
Sure.
Just want to make sure I have a solid grasp of what they mean. Welcome back to the deep dive. We've been exploring this reactivity series, and I'm really starting to see how it's like a master key that unlocks so much about how these metals behave. But before we wrap up, I really want to revisit those processes you mentioned earlier. Oxidation and reduction.
Yes.
Can we kind of delve a bit deeper into what they actually mean?
Absolutely. So oxidation is the loss of electrons, and reduction is the gain of electrons. And these always happen together. It's like a dance where one partner leads and the other follows.
Right. I remember that mnemonic oil rig.
Yes.
Oxidation is loss, reduction is gain.
Exactly.
But I'm still a little bit fuzzy on how this actually plays out in real-world reactions.
Okay, sure.
Give me some examples.
Of course. So let's start with something we see all the time, rust.
Okay.
When iron reacts with oxygen in the air and moisture, it forms iron oxide, which is what we call rust.
Right.
In this reaction, iron is oxidized because it loses electrons to the oxygen. And the oxygen, in turn, is reduced because it gains those electrons.
So rusting is essentially an oxidation-reduction reaction.
Precisely.
Wow.
And it's happening all around us.
Okay.
Think about burning a piece of wood. The wood, which is mostly carbon, reacts with oxygen in the air, producing carbon dioxide and releasing heat and light. The carbon in the wood is oxidized as it loses electrons to the oxygen. And the oxygen is reduced as it gains those electrons.
Wow, so even something as simple as, like, burning wood involves these fundamental processes of oxidation and reduction.
It highlights how important these concepts are in understanding the world around us.
Yeah.
And the reactivity series helps us see how readily different metals will undergo oxidation.
So metals higher up on the reactivity series are more likely to be oxidized.
Yes. That's why metals like potassium and sodium, which are at the top of the series, they're stored under oil. Because if they're exposed to air, they would react so violently with the oxygen that they could even catch fire.
Really?
On the other hand, metals like gold and platinum, which are at the bottom of the series, they're very resistant to oxidation. That's why they retain their shine for so long. And are considered precious metals.
This has been an incredible journey. I feel like I've gained like a whole new level of understanding of how metals actually behave. The reactivity series isn't just a list. It's like a powerful tool.
It is.
For predicting and explaining a vast range of chemical reactions.
It's been a pleasure sharing this exploration with you.
Yeah, this has been great.
And remember, the reactivity series, it's just one piece of the puzzle. In this vast and fascinating world of chemistry.
Of course.
But it's a fundamental concept that lays the groundwork for understanding so much more.
And that's a wrap for this deep dive. We've gone from a simple ranking of metals to, a deeper understanding of oxidation and reduction. Displacement reactions. And even how we extract metals from the earth.
It's been a great journey.
It has. I hope you've enjoyed this deep dive as much as I have.
Me too.
Until next time, keep those electrons flowing.